Okay, so at the end of the last part of the lecture, I very inelegantly moved on to talking about how sodium and potassium were incompatible. Now we're going to broaden this out and talk about trace elements, which are just way more useful. So, yeah. We had talked about in previous lectures that certain elements can be incompatible during crystallization, and we kind of talked about this bit in the practical, where we talked about the fact that olivine takes in magnesium first, preferentially compared to iron, and then your melt gets more iron-rich, right? So if a mineral is excluded from if an element is excluded from a crystallizing mineral, we call it incompatible. Right at the end of the last lecture, we talked about sodium and potassium, which are both incompatible during mantle melting. So this is similar to the crystallization thing, but instead of being concentrated in the melt as you form crystals, it's that as soon as you start to melt, these elements go into the melt quite quickly. They're excluded from the mantle residue and they go into the melts. The problem with using sodium and potassium, and we kind of briefly talked about the fact that alkali basalts have higher concentrations of sodium and potassium, and that means that they're lower degree melts. The problem with using major elements for this is that as soon as you start crystallizing a phase that concentrates these major elements, something like plagioclase, it can actually get quite hard to compare between different basalts. You then have to correct for how much plagioclase is crystallized and this kind of thing. So ideally, we'd want to use elements that are less affected by what's crystallizing if we want to study what's going on in the melting regions. So this is going to spawn off this huge lecture in a bit of talking about trace elements, and we'll start off just talking in really general terms about what a trace element is and the concept of compatibility. So everything we've dealt with so far has been major or minor elements, and I've put boxes around them here on the periodic table. The ones in red are almost always major elements in igneous rocks. The orange ones are often minor elements. Some of them can be trace elements, some of them can be major elements. But if you look at how much of the periodic table we've covered there, we've left a lot of real estate unused. So these are all the elements with concentrations more than 0.1%. Just to remind you, 0.1 to 1% is a minor element, and more than 1% is a major element. So trace elements have less than 0.1 weight% in rocks, and it's basically everything else. So we have a lot of periodic table that we can use, and a lot of different elements with slightly different characteristics, and we can look at each of these and try and build up a picture of what's going on by looking at lots of different trace elements simultaneously. All right. So trace elements are different to major elements in that they do not control what minerals are crystallizing from a melt. So these basically just squeeze in wherever they can. And we talk about compatibility being whether they're able to squeeze into the mineral sites that are available or not. So every mineral is made up of different, usually silicate minerals. They're built up of these silica tetrahedra, and I think you will have learned about this in mineralogy. Sometimes you have the isolated tetrahedra, sometimes you have the chains, sometimes you have the sheets, sometimes you have the frameworks. And in between those you have cation sites that, in this case, on the right, I've shown structure of olivine. Olivine has an M1 site and an M2 site. And basically every mineral has kind of a preferred cation size and charge. And every site in a mineral. So minerals with several different sites, they'll have different, those sites won't necessarily have the same size and they won't necessarily have the same preferred charge. So in olivine, the kind of ideal size for an M1 site is about 0.72 angstroms, and angstrom is, sorry, that should say 1 times 10 to the minus 10 meters. So it's 0.1 nanometers. It's quite a useful unit for talking about atoms and crystal lattices and stuff, because it's a similar size to what a lot of atoms are. So 0.72 angstroms, and it prefers a 2+ charge. The M2 site is almost exactly the same size, again about 0.72 angstroms. It's actually a tiny bit larger, but it's kind of rounded off in this one. And that also wants a 2+ charge. And in our tetrahedra, the ideal site is really, the ideal size is very small, it's 0.26 angstroms, and it's a 4+ charge. And so when we look at different ions, we can compare the ionic radiuses to these kind of ideal sizes. And ion sizes depend on atomic number. So generally, the heavier the element is, the higher the atomic number, it's going to have more protons. That means it's going to have more electrons surrounding it. And it's basically the number of electrons that broadly controls the size of an atom, right? You add on more electrons, it's going to get bigger. It's also controlled by the charge. So the greater the positive charge, you can think of it as basically the fact that there's kind of spare positive charge on the nucleus means that the electrons get like sucked in closer. And then the last thing is the coordination. And so this is how many other ions surround it. It's also dependent on the actual ion that's coordinating it. So so these cations are positively charged, so it'd be the type of negative ion that's connected on the other side on the other side of it. So this is mostly going to be oxygen in rocks. So when we look at, this is just a list of different ions, and it's different ionic sizes with coordination number. And the M1 and M2 sites in olivine are what they call octahedra. So these are actually, even though it says octa, they're connected to 6 other ions. And so if we look up the coordination number of the ionic size of manganese, iron, and magnesium, with a coordination number of 6, so we're octahedral, you can actually see that the ionic radiuses, or radii, are very, very close to the ideal size in olivine. So these all fit really well. Magnesium's perfect, 0.72, great. Iron's a tiny bit bigger, but it still fits pretty well. Manganese is a tiny bit bigger, but it still fits pretty well. If we look at some of these other ions, like potassium here, it has a very, very large ionic radius. It's also only got a charge of +1, so potassium does not fit well in olivine. All right, it's too big, and it's the wrong charge. If we look down the other end, we can see here that silicon 4+, when it's fourfold coordination, so that's a tetrahedral coordination, has an ionic radius of 0.26. So again, that fits perfectly in olivine. So almost everything in the olivine tetrahedral site is silica. Is everyone on board for now? Yeah. So basically, things are going to be very compatible in a mineral if they're close to the ideal size and they have the right charge. When we look at, this is kind of a representation of the periodic table, but shown as ionic sizes. The bigger circles are the size of the atoms, so this would be a neutral atom, it's not charged. And the smaller ones inside are the size of the ions. And then they're colored based on whether they're metals, semi-metals, or non-metals. I don't think you need to worry about that too much. But it also shows on this table the kind of typical charges. So this is, on Earth, say like in the mantle, most of the iron is Fe2+ in the upper mantle. Magnesium is pretty much always Mg2+, sodium is usually 1+, okay? So with all these different sizes and charges, we have a lot of different options for what we can fit in and how, yeah.
And if it was incompatible, it meant that it will never crystallize? It will always go back into the melt?
Yeah, so in general, as we're crystallizing a mineral, elements that are incompatible in that mineral will be concentrated in the melt.
Okay.
Yeah, because we're removing other stuff from the melt, but we're not removing that, so the concentration goes up.
Like they can't crystallize, or they just...
So the point in what I'm saying here is that it's dependent on what's crystallizing. So obviously we talked about potassium's too big for an olivine site, but for alkali feldspar we know that has potassium by definition. Yeah. So alkali feldspars have a site that's nice and big for potassium.
So it can crystallize.
So it can eventually crystallize, but as long as we're crystallizing stuff like olivine, clinopyroxene, plagioclase, calcium-rich plagioclase, then potassium is going to be incompatible.
Okay.
Yeah. Okay, so because we have this huge variety of different mineral structures, and each mineral has different sites with different ideal sizes and kind of ideal charges, then different elements are compatible into different minerals. So just put a few different structures. Here's feldspar. Feldspar has these framework silicates, right? These are the silica tetrahedra, blue and kind of purplish colors. Those are mainly silicon with a bit of aluminium. And then in between we have these big gaps where we can fit large potassium 1+ ions. And because in this one, in feldspar, we have a potassium and an aluminium, that's a 1+ and a 3+, that makes up the same charge as one of these silica tetrahedra, so everything's nicely charge balanced. This is an olivine. These are olivine just has these isolated silica tetrahedra. They don't touch each other. They don't make chains or frameworks, and it has quite small cation sites, and we could fit magnesium or iron really easily in here. And then diopside, which is pyroxene, we have those chains of silica tetrahedra, and in some of the sites they're quite small, and you can fit magnesium and iron pretty well, and in some of the sites they're a bit bigger, and we can fit calcium. And so that's why we would often write diopside formula as calcium, and then brackets magnesium or iron, and then Si2O6. All right. So this is where we start doing a tiny bit of maths, which will ramp up, but I hope to make it not too dramatic. So we can use a partition coefficient to describe whether an element is compatible or incompatible. And usually in igneous rocks, the partition coefficient is just defined as the concentration in the mineral divided by the concentration in the melt. So pretty much nothing has a partition coefficient of 0. Nothing that I know of. They just get very, very small if things are highly incompatible. So the reason for that, if it's incompatible, this concentration in the melt is going to be very high, and the concentration in the mineral is going to be very, very low, and so we get a very small partition coefficient. Yes, Oscar?
Just so the concentration is that you pick a certain element and then you put it in both in the melt,
yeah,
from the melt and the mineral.
Yeah, so the way I wrote this here, D, this is the symbol for it, mineral divided by melt of this element.
All
whatever.
Right,
Yeah.
Yeah.
So if we have something that's compatible, it's going to be very high in the mineral compared to the melt, and so the D is going to be large. So yeah, basically if the partition coefficient, if this D is greater than 1, then it's compatible. If it's less than 1, we call it incompatible. And if it's a lot less than 1, then we say highly incompatible. I don't know if there's kind of a hard boundary between what you call incompatible or highly incompatible, but the example I've given here, this is a partition coefficient for rubidium, which is another large 1+ charged ion. It's kind of similar to potassium. It's in the same group in the periodic table. And the olivine basalt partition coefficient for rubidium is really tiny. So this would be considered highly incompatible. By contrast, the olivine basalt partition coefficient for nickel is quite high. So that's compatible. Yeah?
There's an implication there that this coefficient is more or less constant, no matter how much the concentrations are.
There is.
It is.
Yeah, we'll talk about that in a sec.
There's not a saturation point, or.
Yeah, so this is why we're using trace elements. But that's a really good question. Have you done chemistry before, right? This is no, okay, just a genius, all right. Okay, so Leonard predicted my next slide. So you can only use partition coefficients like this for trace elements. And so, as I said right at the start, these trace elements are just trying to fit where they can. They're not controlling what minerals are forming. So basically, trace elements are very, very dilute. So when I add a trace element to a mineral, if I add another trace element, they're not really interacting with each other. One's over here, one's over here. There's loads of space, and there's not many trace elements. So they're spread out, and the effect of having more of that trace element in doesn't affect the subsequent trace element that you're trying to put in there. So basically we treat this as the trace element ions do not interact with each other. And this is something called Henry's law, which actually comes from chemistry, and it's based around gases, but we use the same principle in geochemistry. And so if we plot this up as a graph of concentration in the solid against concentration in the melt, and we just start increasing the concentration in the melt, and we see what happens to the concentration in the solid. In an ideal world, we just get this straight line. We keep adding to the melt, and we keep increasing the solid. But what really happens for a lot of major elements is we get this, they call it non-ideal behavior. So as you increase the concentration in the melt, it's not linear, right? We get some other effect, and this could be the fact that maybe once you've already put some of that element into a mineral, it changes the structure. It could be, it can go either way. It could actually make it more appealing for more of that mineral to come in. But the point is, we can't just use a fixed ratio between the two. The nice thing is, down at very, very low concentrations, this non-ideal behavior basically approximates a straight line because of what I was saying before, because these different ions don't interact with each other. So we increase the concentration in the melt, we're going to increase the concentration in the solid. Going back to this example here, olivine over basalt, it's this 0.02, so, 0.002. If we had a rubidium concentration of 50 in the basalt, then we would get some concentration in the olivine, and if we double the concentration in the basalt, we double the concentration in the olivine. So these different rubidiums are not affecting each other, and so we can use this linear relationship down here. But yeah, that all falls apart at high concentrations, so this is kind of why trace elements are more useful to deal with for this stuff than major elements. I think we can think about this non-ideal behavior a bit with the, if you remember back to the olivine binary, where we had that magnesium and iron, and it kind of made that envelope like that. So the ratio between the amount of magnesium in the melt and the amount of magnesium in the olivine is not constant, right? If we have 0% magnesium in the melt, then we have 0% in the olivine. If we have 50% in the melt, then we don't have exactly 50% in the olivine. So we're not keeping constant proportions there. All right. So yeah, size of different ions, it depends on the atomic number, charge, and coordination. So how many different ions they're touching. Different minerals have ionic sites with different ideal charges and sizes. Some elements are compatible and in a mineral if they are close to that ideal size and charge, and they would be incompatible if they don't easily fit into any of the sites in the mineral. And for trace elements, we can describe this with this partition coefficient. Does anyone have any questions about that? Okay. Good. All right. So now we'll talk a bit about equilibrium and fractional crystallization. And these are things that I've touched on. I've probably said fractional crystallization a ton of times during this course, but I want to be a bit more formal about it because it's quite important for the trace elements. So basically, we can think about crystallization as two different end-member models. And when I talk about end-members, I mean these are like a hypothetical, pure way of doing things, and the reality is going to lie between these two end-members. But mathematically, we can describe the end-members very easily, so we'll start with that. So the first one is equilibrium crystallization. This is what we used for most of the phase diagrams. Because they're based on experiments that are conducted at equilibrium, people heat something up, they hold it at a certain temperature, they see what minerals are there, they see how much melt is there, all this kind of thing. So for equilibrium crystallization, the crystallization is happening in a completely closed system. So we're not separating melt and crystals, they're just sitting there together. And the crystals are forming in equilibrium with the magma. This means that they're at the same temperature, and that the composition is actually going to adjust as we keep crystallizing, so that the magma and the mineral are always kind of happy together. Showing this here, we start with magma, we've got some little crystals forming. As we crystallize more, the composition of the magma changes, because the composition of what we're crystallizing is different to the original magma. But these early formed crystals adjust their composition so that they're always in equilibrium with the magma. So we're never going to see any zoning in them, right? Equilibrium crystallization cannot produce zoned minerals, because we're basically wiping out this memory of the early formed crystals. Then, as we cool and crystallize more, the magma composition changes further, and the mineral composition also adjusts to match the new magma composition. So yeah, all the phase diagrams we did assumed this. The other end member is fractional crystallization. And in fractional crystallization, we think of the crystallization as happening in these tiny, tiny little increments. And every increment, every little stage of crystallization is in equilibrium with the magma at that stage. But as soon as we've formed that little bit of crystal, it is either removed or isolated from the magma. And what do I mean by removed or isolated? We have two options. There's one, they can sink or settle, they can form a cumulate. So if this is our magma chamber, we start forming something on the magma chamber floor that is no longer in contact with the magma that it crystallized from. The other thing is that you can actually isolate the early formed crystals just by growing more crystal around the edges. So here we have our magma starting at one composition and our first little increment of crystallization, and this looks the same as equilibrium, right, in the first stage. But when we crystallize more, we basically just grow crystal on top of it, or we grow new crystals and dump some old ones. But either way, this original composition from our first increment of crystallization is preserved, and it is not in contact with the magma, and it does not equilibrate with the magma. So what we'd expect here is we should see zoned crystals, and it's possible to have sinking and accumulation. And this picture that I used in the very first lecture was showing fractional crystallization. So we can tell that because we start with the magma that's crystallizing one thing. These are dropping out of the magma and they're keeping their composition. And then we're crystallizing a second mineral, and that's dropping out of the magma and keeping its composition. If this was equilibrium crystallization, some of these early formed minerals would be adjusting with this, and we'd have a mixed composition set of minerals of, say, mineral A, mineral B, and we'd have our magma, and everything's happy in an equilibrium. So this is fractional crystallization. We're forming cumulates with progressively different compositions, and the magma is getting more and more evolved. So in reality, most crystallization that we see is near fractional. And the evidence we have for this is we can actually see zoned crystals that I was just talking to Leonard about. And what I mean by crystal zoning is that we have these progressive layers of slightly different composition. You can see it here in plagioclase, and this is in cross-polar, and it's quite obvious because these actually have slightly different crystal orientations. This is similar to the twins that we see normally in plagioclase, but in this case, it's just different layers growing onto the crystal. We also see cumulates, and we see cumulates, say, like a dunite cumulate, and this cannot be in equilibrium with something like basalt by the time it crystallizes, because by the time you finish crystallizing the basalt, you've also crystallized plagioclase and clinopyroxene and all these other things. But we see this as just a pure olivine cumulate, so that's been dropped out, maybe bottom of a magma chamber or something, and it's been removed from the liquid. So there are exceptions, but most crystallization is going to be near fractional. So now we'll talk a bit about what that means for trace elements. So often we're crystallizing more than one mineral at a time, and that means that we have to go from these mineral partition coefficients, which you can basically just look up online, or for the exercises, I'll give them to you. And you calculate a bulk partition coefficient. And so in this case, it's the mineral partition coefficients. So this is the D, the partition coefficient for mineral 1 over the melt of a particular element, and you weight it by the proportion of that mineral in the crystallizing assemblage. So if we had 70% plagioclase and 30% olivine, and we wanted to find the bulk partition coefficient for rubidium, we need to do 0.3, 30% olivine, times the olivine over melt partition coefficient for rubidium, plus 70%, so this would be 0.7, times the plagioclase over melt partition coefficient for that same element. Yeah.
This is still only trace elements?
Yeah, because we're using partition coefficients. So, yeah. All right, so I've got an example of that here. The partition coefficient for nickel between olivine and basalt is 15, so it's highly compatible with olivine. For clinopyroxene and basalt, it's 3, so it's compatible, but not quite as compatible. And for plagioclase and basalt, nickel is not compatible in plagioclase, right? We're less than 1, so it's incompatible. So if we do our 3 stages of basalt crystallization that we did in the exercise and we did in the previous lecture when talking about major elements, the bulk partition coefficient, when you only have olivine crystallizing, well, it's the proportion of olivine is 100% or 1, and the partition coefficient is 15, so we get 15. That's really straightforward. If we have this plagioclase olivine mixture, we have the proportion of olivine, that's 30%, 0.3, times the partition coefficient for olivine, which is 15, plus 70% plagioclase, that's 0.7, times the partition coefficient for plagioclase, which is ends up being about 4.5. So nickel is less compatible in this mixture than it was in just olivine.
How did you make out the W again? Like the 0.3 and 0.7?
Just because I said there's 70%,
Oh,
so
okay.
that's 0.7, and there's 30%, yeah. And then for our basalt eutectic melt, where we have 50% clinopyroxene, 43% plagioclase, 7% olivine, then I'm not going to talk through it, but we do the same thing, 7% times 15, 43% times 0.1, and 50% times 3, and that comes out about 2.6. So it's compatible in all these different crystallizing assemblages, but it's becoming slightly less compatible over time. Because it's compatible at every stage, then the nickel concentration in the magma is always going to fall during crystallization of basalt. Okay, so we can then move on to these models for equilibrium and fractional crystallization. And I'm always going to start with equilibrium because it's actually, I think it's easier in terms of the maths to understand. So basically we can use either the bulk partition coefficients if there are several minerals crystallizing, or we can just use a single mineral partition coefficient if there's only one mineral crystallizing. And the equations that we use, we always normalize it to the starting concentration because this just makes it a lot easier. If you wanted to find like an exact number, then you just move this to the other side, so you times everything by the original concentration. What this is saying is the concentration in the melt, the liquid, so Cl, divided by the original concentration in the liquid, because we started with something that was probably 100% melt, equals 1 divided by the partition coefficient, or the bulk partition coefficient, plus the fraction of liquid, the fraction of melt that's left, times 1 minus the partition coefficient. And you don't need to memorize this equation, but we'll probably try and use it in the exercise this week to calculate some stuff. In the solid, it's almost the same equation. So this is the concentration in the solid divided by the original concentration in the liquid, and it's the same but just multiplied by this partition coefficient here. All right. Fractional crystallization is the same idea. The equations are slightly different. So in the melt, concentration in the melt in the liquid divided by the original concentration is the fraction of liquid or melt that's remaining to the power of the partition coefficient minus 1. In the solid, it's the same thing but multiplied by the partition coefficient here. Okay. So that's probably quite abstract on its own, but just show you what this looks like. So on the left here, we have a plot of the concentration in the liquid divided by the original concentration for a range of melt fractions remaining. So on the left here, we have 100% of the melt remaining, so we've not crystallized anything at all. On the right here, we have 0% of the melt remaining, so we've crystallized everything. And this is shown for a range of different partition coefficients. So the K is 20, so in these diagrams it just uses K instead of D like I've been using, but it's the same thing. So K is 20, this is very compatible, and what happens is as we start crystallizing, the concentration that's left in the liquid drops rapidly and eventually gets really, really low. That makes sense. So this is something like nickel, we're crystallizing olivine, we're pulling nickel out of the melt and into the olivine, the concentration in the remaining melt drops. If it's highly incompatible, so here it's shown with a partition coefficient of 0.01, then as we crystallize, we're not pulling any of that incompatible element into the solid. So it just sits there in the melt, but the amount of melt that's remaining is going down, so the concentration goes up and up and up. Okay? This dashed line here is just showing what happens in the solid, and this is for something with K is 10. So the first solid to crystallize, the partition coefficient is 10, so the concentration in the solid is 10 times what it is in the melt. So it's at 10. If we start at 1, then it's at 10. And in the first solids that crystallize, we have very high concentrations of this compatible element, but we actually start to run out of that compatible element in the melt because we're putting it into the solid. So the later solids actually have less and less and less, and then when it's 100% solidified, this the concentration in the solid has to be the same as the original, right? Because we haven't lost anything from the system. For fractional crystallization, this is basically the same plot, but you can see that there's a log scale on the bottom. And here, if you have something that's highly compatible, it drops crazy fast. And the reason is because as soon as we crystallize that mineral, we remove it from the system. And so there is much less, say, something like nickel, compatible element, sat around in the melt, equilibrating. It's gone. It's gone into the minerals and it's removed. So essentially this just drops really, really fast. For a highly incompatible element, as we're crystallizing, we're concentrating it in the melt as well. We actually end up at the same place in both of these. So particularly for the melts, you can see that in a highly incompatible element, the last increment, when we're 100% crystallized, the last increment of melt is up here close to 100, and with the equilibrium ones, the last increment of melt is up here close to 100. And that's because if we've got 1% melt left, then we have to have all of the original incompatible element in that last 1% of melt. Yep.
What was the 100% at the top? Is that still melt and...
This is concentration. So this is percentage of crystallization. This is concentration. And in these curves, it's in the melt. So if we have 99% crystallized, then we have to have all of that incompatible, almost all of that incompatible trace element in that last 1% drop of melt.
If what,
So,
sorry?
This is highly incompatible, right?
Okay,
At
yes.
0.01.
Yeah.
So if we crystallize 99% of this melt, then there's 1% of melt left, and that has to hold almost all of this incompatible element. So the concentration is basically 100 times higher. Does that make sense? Yeah, Oscar.
What happens to that 1% melt? Does it just exist in like purgatory?
No, so if it eventually crystallizes, then the average solid will have the same concentration as the starting thing.
Okay.
Yeah. So in both of these cases, in terms of the liquid at least, we actually kind of end up in the same place. In terms of the solids, it's a bit different because in this one we're removing them. Yeah, Lauditz.
So the dotted line, that was for the solid.
That was for the solid, yeah.
What's the difference between the solid and the 100% crystallized? Isn't that the same? Or
Yeah. So I was talking about this was the last drop of melt before we're 100% crystallized. But yeah, when we've 100% crystallized this solid, the average composition of the solid is the same as what we started with.
that's my question, because the crystallized, wouldn't that be the solid?
Yep.
A solid is always 100% crystallized, right?
Yeah.
So how can it be 0% crystallized? Is that
Oh,
just
so no. Yeah, I see what you're asking. These are. How do I explain this? These are two different curves, right? This is what's happening with the liquid. As the percentage of liquid drops, this is what's happening with the solid as the percentage of solid increases. So at this line, if I draw it from 0.8, we have crystallized 20%. So that's the composition. Let's do it both for k equals 10. That's the composition of the liquid after 20% crystallization, and that's the composition of the solid after 20% crystallization. Yeah, and these are in equilibrium. So these things are paralleling each other. And the ratio between these is going to be the partition coefficient. Any other questions? Yeah?
Incompatible elements will always crystallize last.
Yeah, unless something changes about the crystallizing assemblage. You keep concentrating them to melt until everything freezes, unless you eventually crystallize a mineral that they are compatible in.
Oh, yeah.
And that's generally what happens, right? Like, potassium's incompatible, and then you eventually get alkali feldspar because you got so much potassium, it's got to go somewhere. Yep.
And this is like each for their own melt. Like what is happening with all the incompatible and compatible elements?
So this is quite abstract. So these curves are just for like an imaginary element that had a
Okay.
partition coefficient of that.
So it's not for the same melt of what is happening
each one of these curves is for, it could be for the same melt if you had elements with these partition coefficients in the same melt. But I don't think it matters. It's probably best to think of them as just isolated. Yeah, like this one's basically nickel, this one's basically rubidium.
Okay.
Yeah. Okay, so in terms of the liquid, we end up basically the same place. The last little drop of melt has a really high concentration of incompatible elements. But in terms of the solid, in terms of compatible elements, they're basically gone immediately with the fractional crystallization, whereas there's always some hanging around in the melt in the equilibrium. Now, the steepness of these curves is going to obviously depends on the partition coefficient. If you had something that was infinitely compatible, then it would be just like a step. It would just go down immediately. But we don't have that in reality. So yeah, I think the key thing to remember here is that in both of them, the concentration of incompatible elements increases in the melt as you're crystallizing, and the concentration of compatible elements decreases in the melt as you're crystallizing. But the fractional crystallization, these changes are happening a little bit more quickly because we're removing stuff. All right. So equilibrium crystallization, the crystals and melt remain in equilibrium as the magma crystallizes. This is like most of our phase diagrams that we looked at. Fractional crystallization, we're either removing or isolating the crystals as soon as they form. In reality, most crystallization is near fractional. For both these styles, compatible elements are going into the minerals and incompatible elements are being concentrated in the melt. But fractional crystallization causes the more rapid changes. You'll sometimes see this described as fractionation. Fractionation is just any process that separates one element from another. All right. Any more questions on that? Yeah?
Potassium is not a trace element.
No, it's not.
Why is it then on the chart before? Didn't
The table that I showed back here?
the one that we just looked at?
The one we just looked at.
With the fractional and
Oh, right.
crystallization.
Yeah, so this K is actually just another. Some people use that instead of D for the partition.
Can we use the potassium as an example for?
Yeah, sorry.
Incompatible?
Yeah, that's my bad. Yeah,
Oh, okay.
but even so for trace elements, yeah, if you because in reality you never. How do I explain? For trace elements, they will keep increasing in the melt until the last little bit of melt, and if that freezes to a glass, it'll be super high in all these incompatible trace elements. It may never crystallize a mineral, or you might get something really, you might get something like apatite, and then you'll get a bunch of these trace elements going and sitting in it, or monazite, or these weird like last little bits. If it doesn't freeze to a glass, then you'll usually get some mineral that will take up all these incompatible elements. But yeah.
Can't all elements in theory be trace elements if there's just like small enough amount?
Yep. It's just that in most rocks we're fairly like silicon is almost never a trace element in rocks,
Okay.
but maybe in a limestone it might be. Yeah.
Okay, and the reason that the mineral user apatite can have all these trace elements in it is not because apatite is particularly good at having all kinds of trace elements. It's just because it's what would crystallize.
No, it is actually, so that would have a particular mineral site that some of these trace elements can sit in.
Okay.
I think, even, so later we'll talk about rare earth elements. They're not compatible in many things, but then late on in crystallization you can get these weird things like monazite, and monazite will take up rare earth elements. But this isn't something that we're normally going to worry about. For a lot of these things, when I talk about them being compatible or incompatible, I'm usually going to be talking about like fairly normal, like mafic to intermediate crystallization. Again, like going back to the example of potassium, which isn't a trace element, but I think it's a good example. Like eventually we'll crystallize alkali feldspar, and then it might begin to drop in the melt, or we'll crystallize biotite and it might begin to drop in the melt. So things are only compatible or incompatible based on the mineral assemblage that's there. All right. So now we're going to go slightly more complicated, and we'll talk about equilibrium, which is sometimes called batch melting, and fractional melting. All right. I briefly mentioned this in the first lecture, and I don't know if it was the right time or not, but we're coming back to it. So, yeah. So this is very much the same idea as for the fractional and equilibrium crystallization. So, for equilibrium or batch melting, we are producing a melt, but it's staying in contact with the solid. And because it's staying in contact with the solid, it's chemically exchanging with it, it's the same temperature. And as you produce more melt, both the composition of the melt and the solid are going to adjust so they're always in equilibrium. For fractional melting, as soon as you make a tiny increment of melt, it's gone, right? And in the mantle, I think we talked about this is because basically the melt is less dense. It just gets squeezed out. It's like wringing water out of a sponge, right? It's less dense. There's the kind of weight of mantle above it, and it just pushes it out. So you form a tiny bit of melt, and it goes. We also have this dynamic or critical melting. That's this kind of intermediate process where we make a bit of melt, and it sits around. So this is like batch, but if we make too much melt, then it goes. So we're left with some melt that escapes, and some little bits of melt that's trapped in between. For fractional melting, it's similar to the fractional crystallization. Each increment of melt is in equilibrium with the solid that it formed from. But as we carry on melting, the composition of the solid is changing because we're removing melt from it. These increments, again, in reality, they might just escape as a small little blip of melt, or they might mix somewhere higher up the system, say in a melt channel or something like that. All right. So for equilibrium melting, this is actually the exact same equation as for equilibrium crystallization. And that's because if everything's in equilibrium, it's completely reversible. It doesn't matter if we start with a melt and cool it, or if we start with solid and heat it, we're going to get the same, at the same temperature, we'll have the same proportion of melt and solid, and everything is, you can do it either way, it doesn't matter. But the big difference here is we're starting with the solid, so our original concentration is the concentration 0 in the solid. So otherwise it's identical. In the solid, it's again the same, but our initial concentration is the concentration we started in the solid before we started melting. So I've kind of listed all that out. I'm not gonna read through it because it's just the same, and that's just so that when you look at this, you can see what all the symbols mean without having to jump forwards and backwards in slides. All right. Now, if we just use a bulk partition coefficient for a solid with several different minerals in it, then we're implicitly assuming that the melting is modal. So let's say if we have a mantle peridotite and it's whatever, 50% olivine, 25% orthoperoxine, 20% clinoproxine, and 5% spinel. If we just calculate the partition coefficient for each one of those minerals and weight it by the amount of each one of those minerals, so 50%, 25, 20, and 5%, then we're basically saying that every single one of those minerals is melting by the same proportion. Now, in reality, as we talked about before, melting is non-modal. So if we start with our lertzolite, our fertile mantle peridotite, we make a basalt. The basalt composition isn't the same as the lertzolite composition, so we must be melting more of some minerals than others. This is in terms of major elements. So here you can see the basalt composition. This is a forsterite, so olivine, diopside, clinoproxine, an enstatite diagram. So the basalt is much closer to this clinoproxine, orthoproxine join. So we're melting more of the pyroxene and less of the olivine. And when we make this basalt, we eventually get rid of all of the clinoproxine and make a harzbedite. So we can see from that we're not melting all the minerals equally. So in this case, we're melting more clinoproxine, more orthoproxine compared to olivine. So there's a slight modification of this equation, which I think it doesn't need to be as complicated as it looks. But basically, we use these partition coefficients that are weighted by the proportions of the mineral that are entering the melt. So if we split up the composition of the melt and say how much is coming from olivine, how much is coming from pyroxenes or whatever. So instead of it being, olivine's 50% in the rock, so it's 50% in the melt, it would be maybe 20% in the melt, or 10, right? If we do a ternary thing, we don't have a lot of olivine entering the melt. So this is basically the same thing, but these P's are the fraction of the mineral that is in the melting assemblage, not the fraction of the mineral in the original rock. And so this melting equation is virtually the same, but instead we have this D0, which is the initial bulk partition coefficient, and we have this P here, which is to do with the proportion of each mineral that's the proportion of the melt that is coming from each mineral. Now, this p-value can change. Yeah?
I don't really get the initial bulk partition coefficient.
Oh yeah, so this is just the partition coefficient when the melt fraction is 0. So the reason for this is that this can change. So if we were to do this melting equation, and we started here, and again, this is what it looks like for major elements, but we're doing it for trace elements. So we start off calculating the partition coefficient with whatever proportion of minerals that are melting. But maybe after 20% melting, all the clinoproxene is gone. This P is then going to change because suddenly the P for clinoproxene goes down to 0 because there's no clinoproxene left to melt. So we use this initial one, and the reason for this is it's quite handy because we can approximate like a very small degree melt as the melt fraction being 0. And then the concentration in the liquid divided by the original concentration is 1 over the partition coefficient. So I'll talk about that a bit in a sec, but it helps simplify it down a bit. Yeah. Okay. In the last example for crystallization, I think fractional crystallization equations are a bit more simple, but they're more complicated than the equilibrium melting. And here we have concentration in the liquid divided by the original concentration in the solid is 1 over the partition coefficient times 1 minus the fraction of melt that's been formed to the power of 1 over the partition coefficient minus 1. Again, you don't need to remember this, but we'll try some calculations with it in the exercise. Yep.
So the non-modal from the other slide that was just there, that's still in equilibrium?
That was equilibrium, but non-modal, yeah. In the solid, it's just a tiny bit different. Again, we've multiplied everything by d, so this 1 over d disappears. All the same symbols as the previous, the slide 2 slides ago. For non-modal melting, again, you don't need to remember this, but essentially we're doing the same thing here. We're using this P again to weight the different minerals by the amount that they're contributing to the melt, not by the amount that they're in the original rock. Yeah. Now, in terms of the maths, these fractional melts are what we call infinitesimally small melt fractions. So they are this is the composition of the melt as the melt fraction tends towards 0, so they're tiny. In practice, if that was the way melting worked on Earth, then we'd expect all these midget volcanoes, like a centimeter tall or something, and that doesn't happen. So in practice, what actually happens is that we have probably quite close to fractional melting because, again, we remove melts quite efficiently from the mantle as soon as they're formed. But they probably aggregate in some way. So this means they're kind of like clumped together. And we talked about this in the very first lecture where, you've got some small amount of melting beneath the mid-ocean ridge, and then these little melts percolate upwards, they form melt channels, and then they get focused towards the ridge, and they get removed. So there are equations for the aggregate fractional melt. I'm not going to talk through them, but they're here in case you need them. And this is basically doing the job of adding up all those little melt fractions to make a mixed aggregate fractional melt. All right, and this is probably the most important thing about slide about the whole thing here. So these are the same plots as before, but for equilibrium melting and fractional melting. So here, the melt fraction is increasing to the right. In the other one, the melt fraction was decreasing to the right because we were crystallizing. In this one, we're melting. So if we have something that is highly incompatible, for equilibrium melting, so if it was perfectly incompatible, it has a bulk partition coefficient of 0, right? It doesn't fit in the solid at all. And basically, as we melt a tiny bit, all of that incompatible element gets removed into the melt. And as you carry on melting, it's actually getting diluted down. So this is the extreme case where it's perfectly incompatible. This is a more standard incompatible element. The bulk partition coefficient is 0.1. And so if we start with a concentration of 1, then the very first melt that forms has a concentration of 10. And again, we can do that by just making F0 here. And if we make F0, then we get 1 over, and this is using KD instead of D, 1 over the partition coefficient is 10. So the first melt formed is going to have very high concentration of incompatible elements. As we carry on melting, they'll get diluted down. Once we've melted 100%, it doesn't matter whether it's compatible or incompatible, we have to have the same concentration as what we started with. Okay? For fractional melting, it's a little different, but if we go back to the fractional melting equation, which was here, we actually get the same thing. Is if we set this FL, so the fraction of liquid, to 0, we just get 1 over D times 1 to the 1 over D minus 1. So what this ends up being is that the first melt formed, again, for a bulk partition coefficient of 0.1, it's just 1 over the partition coefficient times the original concentration. So the first fractional melts are very high in incompatible elements, but because we're removing this melt from the system, unlike the equilibrium one where the melt is sticking around, after a certain amount of melting, we actually just completely get rid of those incompatible elements. They're just gone from the solid. And so the last melts to form actually have none of these incompatible elements because they've already been taken out of the system. Yep, Nadia first.
You said that you're getting rid of the melt and you're not getting rid of the solids?
In fractional melting, we treat it as if we have a solid there, and as soon as you make a melt, you remove the melt.
Okay.
In fractional crystallization, we treat it as you have a melt, as soon as you make a crystal, you remove the crystal. Yeah.
You said for the equilibrium that at the end, when you had 100% melt, that it would be the same concentration?
Yeah, as what we started with. So if you take a blob of mantle and you melt it 100%, you now have the exact same composition, but it's 100% melted.
Okay, so same composition, but
Yeah.
you still don't have the same concentration, do you?
This is 100% melt, and so
But doesn't the concentration fall? Isn't that what it's showing?
no. So this at 0% melting, if you imagine these as a suite of different elements with different partition coefficients, they all have a concentration of this C naught S.
Yeah.
So because we're plotting this as concentration of the liquid divided by this, they'd all be at 1 when it's 100% solid. As soon as you start to form a melt, the incompatible elements are very high in the melt, the compatible elements are very low.
Right, so they
But if you melt everything 100%, it all ends up at 1 again.
Yeah, okay, so
Yeah.
they all make up 1, and
Yeah.
then at the end you still have 1.
Yeah.
Yeah.
Yeah, exactly.
Okay, so you have to like add them together, or?
No. Imagine these are different elements, but this is showing that it doesn't show like the 0%. It starts with a melt here. At 0%, the concentration, well, there would be no concentration in the liquid, so everything would be the original concentration in the solid. So in this case, because we're normalizing to that, everything would be C naught divided by C naught, which is 1. So for a compatible element, if we're doing equilibrium melting, the first form melts are quite poor in that compatible element, and then as we melt more and more and more and more, we're basically concentrating that compatible element in the solid that's left behind. And so even though it's still compatible, as we get towards the high melt fractions, it starts to come into the liquid in an appreciable amount, and if we melt 100%, again, we end up at 1. With the fractional ones, you can see a couple of examples here, but they're just for the, so here's for a compatible element. So it's actually pretty similar, but because we're removing it, the concentration of this compatible element in the last liquids gets really extreme, because the last solid is going to be close to 100% of these very compatible elements. Again, you can see the same idea that fractional crystallization kind of causes these more extreme or more rapid changes than the equilibrium. Sorry, fractional melting causes more rapid changes than the equilibrium melting. Okay, so this is really useful, although it seems pretty abstract at the minute. So the way we can use this is that during melting, incompatible elements are highest when the degree of melting is low. And then as the melt fraction increases, the subsequent melts that we're adding don't have as many of these incompatible elements. So we actually reduce the incompatible element concentration as the melting progresses. During crystallization, the incompatible elements are lowest when we just have our magma that's just made it, to a crustal magma chamber or something. And as we crystallize, we are not putting the incompatible elements into the crystals. So we're removing crystals, we're concentrating those incompatible elements in the magma that's left behind. So basically what we can do is if we pick a combination of different incompatible trace elements with different partition coefficients, we can use this to establish what degree of melting we needed to form a melt and how evolved the melt was. This is how much crystallization has occurred. Okay. Yep, so the main point there is equilibrium melting, basically the same as equilibrium crystallization. Solid residues in the melt remain in equilibrium. For fractional melting, as soon as you form a melt, it's gone, and these might aggregate, they might mix together somewhere higher up the system, like in our melt channels beneath the mid-ocean ridge. Most mantle melting is near fractional, and it's something that we call critical melting because it's not pure fractional, but it's pretty close. And for both styles of melting, we have more compatible elements concentrated in the solid as we make melt, and the incompatible elements preferentially go into the melt. And again, fractional crystallization causes these more rapid change. Sorry, fractional melting causes more rapid fractionation of elements. Okay, does anyone have any questions about that? Okay, I think that's it. Yeah, so thanks for staying with me through that. I'll just leave that up for a sec, and then the next part of the lecture, I think we'll get into, it'll probably be a bit more practical and a bit more obvious how we can use this, and then just to end, we'll talk about large igneous provinces again, just so we can look at some pictures and not deal with maths.